Okay, we're going to talk about, this might be also be a review for some of you, and why the cross product is actually an area. The cross product represents, it encapsulates area, surprisingly, because it's completely not obvious. The fact is that if you have two vectors, b and a, then they induce a parallelogram, which you can draw by you can copy b as a ghost, and you put it on the tip of a, and you can copy a as a ghost and put it on the tip of b. And that parallelogram, the area, is encapsulated by the cross product in the following formula. If you take the cross product, which is an algebraic operation, you take that length, that actually gives you the area of the parallelogram, P. And this is kind of surprising, and it's also extremely useful because we know from a previous video that in 1D we used the length of line segments to get the length of curves. And so what we'll do in 2D eventually is we'll use the area of parallelograms, and that'll give us the area of surfaces. So for now, let's just content ourselves with asking, how do I get the area of these parallelograms? And that's with the cross product, and I'll show you why. So what I'll do now is I'll give an easier proof than you might see elsewhere. So how you do this is, note that if we're in 3D, right? So the vectors can point in weird 3D directions. So what we'll do is we'll just rotate this down into the plane. We'll create two new vectors, A prime and B prime, which share the same area and they share the same angle, in the sense that this angle theta between them, it'll be the same angle when you rotate it downwards, because rotations preserve angles and areas. And what I mean by area is, if you draw that parallelogram, let's imagine that's a parallelogram, then that parallelogram will still be a parallelogram when you rotate it. It just doesn't look like it because I'm not drawing it nicely. So the area will be area prime. And so it suffices to do an easy situation. So now we're in the xy plane because we rotated downwards. And what I'll do now is I will draw A on the x-axis. And then I'll just draw B like so. Any other orientation, you could rotate to this, right? So all we need to do is find the area of this parallelogram and show it's equal to the cross product. Well, actually, the area of a parallelogram is quite straightforward, right? Because the area of a parallelogram, it is actually just the base times the height. Let me just get this axis back on here. The area of a parallelogram is actually just the base times the height, right? So it's base times the height, and this will be, in this case, it'll be A times, what is this? The height will be B sine theta, right? So we should expect something like AB sine theta. And I'm, of course, saying that A is just, I'm denoting it as the length of A, and B is the length of B. So we should get that when we use the cross product. So the claim now is that AB sine theta is actually the length of A cross B. And this is actually very easy to show. It'll just take two lines. So let's write this in as a vector. So this will be A times I, and this will be, let's see, I think How about b cosine theta I plus sine theta j? Right? Because what I've done is I put b in polar coordinates. So let's take the cross product. A cross b will be ai cross, I'm going to call cosine theta c and sine theta s because I'm lazy, as usual. bc I plus bsj. Okay? So notice that I cross I is 0. And so all we need to do is I cross j. Obviously, I cross j is k. I cross j is k by the right-hand rule. So we should just get a product of all these factors. So we get a bs times k. But this is actually just a b sine theta. So that's exactly what we wanted to show, that the cross product actually recovers base times height. And again, because we rotated, this applies in general, so we know that this has to be true. The cross product area, the cross product length is the area of the parallelogram it induces. And so this will be very useful for when we're trying to compute area integrals. Thanks for watching.